So I've just been having an extended discussion with Google's AI Gemini all about my physics hypothesis, this idea that a cloud of tunneling electrons falls with the gravitational field of objects, and with its electrons tunneling to within the electroweak range of the nucleus of other atoms over macroscopic distances, and exchanging particles with those nuclei to create the macroscopic force of attraction between two bodies. And like one thing I did get wrong, one thing which Gemini pointed out to me, was that I didn't realise that it was the exchange of a W minus particle in beta decay that causes a neutron, a free neutron, to turn into a proton when it's in traveling in free space. And it turns out that it's a W plus that gets exchanged between the background, I suppose, and a proton that causes it to turn into a neutron. And that's what I was getting mixed up on. But I'm not so certain that this actually destabilizes my model entirely, since I'm thinking that if a neutron is traveling through space, a free neutron, and it picks up a W minus particle, then that neutron will have a de facto minus charge of -1 at a pretty quick juncture, causing it to in fact behave pretty much like an electron. So it will be attracted to the protons in its background, so long as it's not repelled in an equal and opposite fashion by the electrons in its background. So the neutron still curves through space. It follows a curved trajectory through space, falling into a gravitational field. But what I don't know is the exact density of protons versus electrons in the background. It might be that there are protons from other sources, such as from cosmic ray particles, or that the electrons are a little bit more diffuse in the background than the protons are. Because when we're doing an experiment on Earth, for example, and there are sort of electrons floating around in like a cloud out in space as well, it might well be the case that on Earth there's slightly more positive charge than negative charge, very slightly, enough to accommodate the force of gravity, or enough to create something that imitates the force of gravity exactly. And this is an interesting possibility, I think, and I think it's actually quite likely. I think that, when it comes to electrons versus because like all the protons on Earth, like none of the protons are tunneling to macroscopic distances. Only the electrons would be in this model. So, there would actually be slightly more positive charge on the surface of the Earth in the background, if you see what I mean, compared to, for instance, any of the space between Earth and the Moon. Any of the space between the Earth and the Moon would be very slightly negatively charged because their electrons would be dominant. These background electrons would be dominant. So it's trying to figure out the relative densities of charges in different regions of space, and we would have to do experiments with neutrons in space, really, I think, which, I mean, it is an easy test of the model. It's a relatively easy test of what I'm proposing. So that's one thing we can actually do. If it turns out that neutrons' trajectory isn't particularly affected, but it seems almost like a truism to test that, doesn't it? It seems pretty unlikely actually that electrons would be unduly affected by the gravitational force in space, and it seems like they probably would travel in straight lines out there, I have to say, and not really be impacted by the background forces inherent in their environment to such a great extent. Whereas on the surface of the Earth, I'm imagining that, the background density of subatomic particles probably is a little bit more slightly positively charged. I don't want to stick doggedly with my own model necessarily if I'm wrong, if I'm proven incontrovertibly incorrect, because then it would be an exercise in folly, if you see what I mean. But yeah, it did bring up that one point, Gemini did. It brought up loads of other points as well. I might sort of trawl through them, but I mostly wanted to talk about this issue of neutrons, because it's something that is quite often actually brought up by experts and people, well, non-experts as well, commenting on my videos about this. So it's quite a good thing to sort of talk about, I think. The other thing it brought up was neutrinos experiencing gravity. Talking about this, if neutrinos were not affected by gravity, they would have arrived 4.8 months before light, rather than 3 hours before. I'm not so certain that is correct, actually. Well, what does it say? It's about this 1978 supernova explosion, which I actually invoked originally as evidence for my hypothesis, since the light from the supernova was delayed, which caused them to originally think that the neutrinos were travelling faster than light. The reason I suspected for this was because light interacts readily with electrons, so for the star collapsing, the electron density is collapsing back in on it as well, constraining the escape of the light, whereas the neutrinos just flood out straight away instantaneously. And the burst of neutrinos arrived 2 to 3 hours before visible light arrived. If neutrinos were not affected by gravity, they would have arrived 4.8 months before the light. So that is an interesting possibility. And I'm just wondering, maybe the neutral currents exchange between gravitational fields and neutrinos do impart some kinetic energy upon the neutrinos and do delay the escape of neutrinos to some extent. So maybe I was wrong on that also, on a level. So this is a really, really useful exercise to go through the AI, because the AI is actually really good at physics. AI can solve physics problems better than most physics undergraduates. So it's really worth listening to this stuff, I think. But I still don't think my idea lacks merit. I'm sorry to say. I still think the ways in which these particular interactions could take place could very easily mimic what we really anticipate already. So, for instance, when an electron the background electron gets very close to a proton, it's exchanging a W plus or a W minus between the proton and the electron. The W plus and the W minus mutually attract, their masses cancel, and in effect they become photons. So, there is, I think, the shape-shifting of particles going on. Oh, and by the way, they lose their charges as well, because the charges cancel. So the charges cancel to nothing, forming this massless spin-2 gauge field that we're expecting from the graviton. It just seems the most elegant way to me to explain the force of gravity that way. It just does. It still does. It's hard to give up on something, frankly, that you spent over a decade pursuing. But I think the objections are possible to deal with. I think this model represents probably our best chance of explaining the force of gravity. So if it's correct, it's worth sticking with at least. It's worth really beating the idea into submission, if indeed it can be submitted. If indeed it can be beaten into submission. And I'm attached to it because of the utility with which it uses the particles we already have, rather than invoking yet another particle, yet another particle, yet another particle. Because I don't think that's elegant. I don't think that's the way nature really works. It's this economy of particles that I'm looking for in my understanding of physics, gravity. And I suppose if gravity is going to be quantum, then gravitational fields have to have a quantum. They have to have some sort of particle basis. That it has to be a particle ultimately. A gravitational field would be a multitude of such particles. If it is the electron, I think that creates a beautiful avenue towards unification of the forces. In essence, unifying gravity as an aspect of the electromagnetic force. And it fits together a lot more holistically, a lot more naturally, I think. And this idea of on Earth's surface neutrons being exposed to more positive charge. I do think that's true. In that case, it actually assists my model to realise that there's a W minus being exchanged with a neutron, or that it picks up a W minus from the background. I presume an electron is kicked out of the background, and that escapes during beta decay, making beta decay actually yet more evidence that my model is correct, since the electron has to come from somewhere. Where's it coming from? It's coming from the background. This mysterious background superparticles, of which electrons play a fundamental and dominant role. Well, not a dominant role, but play a fundamental and important role. And of course, like most, the matter we observe in nature is a confluence between the electron and the proton, or the electron and the quarks, if we must go there. But so it's brought all sorts of stuff, really. But I can work through most of these things, I think. Yeah, I don't necessarily think this is a bad thing at all. As I said, it's a very useful exercise. It sharpens what I'm thinking into something that can be used better. And it does say at the bottom, Gemini is AI and can make mistakes, including about people. So it can make mistakes, Gemini. It's not perfect. Then again, I'm not perfect either. I don't know everything about physics. I'm sorry to say. I know a lot about physics. I know a lot about physics, cosmology, astronomy, and at this point I do. I have quite a lot of knowledge. But I do make mistakes as well. Everyone does. We're all kind of stupid. We're all kind of limited people, as Feynman said. So these embarrassing little moments where we get beta decay wrong, they do crop up from time to time. But no, like the basis of my model, I still think is sound. I think it's probably a better thing if it is the exchange of a W minus. I think that is the truth still. I think it's tunneling electrons in the background that cause gravitational fields. Oh, it brought up, I'll just do this as well, I'll make the video a bit longer. It brought up the exponential functions governing electron wave functions also, and I brought up the idea of non-locality, and it had a bit of struggle trying to navigate with that idea. It brought up things like conservation of charge, and I think this pretty erroneous notion that an electron would be popping out without any charge somehow after the potential barrier. I really don't see why that's the case, or why it interferes with conservation of charge or continuity of charge, or whatever it was trying to say. There's a lot of text to read through here now, so I'm probably not going to be able to find it again. And we sort of argued the toss about all sorts of points. It was being rather obtuse, Gemini, I think, like a lot of physicists frankly are, and really trying to poke holes in things and shoot things down, rather than trying to make helpful suggestions as to how to make a model work. And physics is a highly competitive field. There's a lot of competition between different physicists, rather than perhaps what it should be, which is more like cooperation. But like to bring up this exponential functions, things like that, the way we've determined that is from standard quantum mechanics before the second quantum revolution. So what this means is like we weren't invoking non-local realism in our understanding of quantum physics, and we naively believe that when an electron A disappears at one point before a potential barrier and another electron B emerges on the other side, we were conflating those two and believing that they were the same electron, whereas the principle of non-local realism shows us that we have no good enough reason for suspecting that they're the same electrons on one side of the potential barrier versus the other side. There's no good reason to suspect that. It's so for all we know, right, that the electron A has disappeared, just gone to somewhere else in the universe, wherever it's gone. We don't know. And the electron B popping up on the other side has emerged from somewhere else in the universe. From where? We don't know. But we thought it was the same electron. We have no reason no earthly reason to suspect that that is the case. That's what non-local realism tells us. And that is now established science. So, like, can't argue with that so much. So where could the electron be in the universe? Like the electron. What do you? It's too mysterious, really, to pin down. If we pin down its position, its momentum becomes infinite. So like measuring it, like of course, like changes its momentum. C'est la vie. That's quantum theory. That's the reality of the situation. You know, yeah, so like exponential functions governing electron wave functions has been rigorously proven by science. It's clearly the same electron on the other side of the potential barrier as well. I can only tunnel a few nanometers. No, not necessarily. We don't know that. Like electron A may have gone into the gravitational field of the planet by some quirk of fate. It just happened to pop up there. Beyond the Van der Waals radius of the planet, or like just somewhere out to near the moon, say, for all we know. And again, for all we know, electron B is just a different electron popping up there. And we have no reason to believe it's the same electron. And I think, Gemini was fumbling a little bit to talk about the continuity of charges. I don't think at any point there's anything physical that suggests that it loses charge. If you see what I mean, when it tunnels. Does it lose charge when it tunnels? I don't think so. I've never really... I don't understand why it would. I don't understand how an electron can ever lose charge. Yeah. So that's the food for thought. That's just a little update on my quantum gravity thinking. I will write a book about this one day, once I've frankly finished working on it, I suppose. Since there's still wrinkles clearly that needed ironing out, but yeah, I don't think it's such a bad development today. Like, but it inspired doubt in me, which is healthy, It proves it's not like a fixed belief, that it's not amenable to change in light of conflicting evidence or incontrovertible argument to the contrary. But what Gemini ultimately proposed was nothing that was incontrovertible. That's the point. Nothing that absolutely eliminates the possibility that this is correct. So it's still very exciting for me to work on this stuff. It's still, I think, a hopeful scenario in terms of looking at gravity. And I think we're on the way to a better understanding of that force. And I am convinced ultimately it is electromagnetic in nature. And the strong and the weak nuclear forces are as well, but we sort of know that anyway. So, yeah, well, we know for the weak force anyway that it certainly is electromagnetic. So thank you everyone for watching. Bye bye. I love you lots. To see you soon.